I think it is 2:05. So let's start. Hello, everyone, and welcome to another installment of our seminar series on models, learning, and sensing in hydrology. Now, the main idea behind this series is to highlight the recent advancements in hydrology through numerical modeling, machine learning, and remote sensing. It is a great honor for me to introduce today's speaker, Dr. Sudhir Kumar. He has seen it has personal value for me since he has seen my whole graduate journey. Dr. Kumar is a research scientist within the Hydrological Sciences Lab at the NASA Goddard Space Flight Center. He leads the NASA Land Information System and the Earth Information System projects, which are comprehensive efforts for water cycle and Earth system modeling by combining computational models and remote sensing. Dr. Kumar was recently awarded the Arthur S. Fleming Award to honor his scientific contributions. Thank you for joining us today, Dr. Kumar. We are very happy to host you. There will be a question and answer session at the end. If the audience members have any questions, please feel free to write them in the chat box or send them to me. With that, Dr. Kumar, the floor is yours.
Yeah, thank you, Javeria. First of all, great to see you again virtually. Thank you for inviting me. So I'm going to talk about some of our efforts towards characterizing the terrestrial water cycle with the tools that we have for modeling and remote sensing and data assimilation, which is basically a technical methodology to combine information from remote sensing and other observational sources with our model estimates. So I just want to also acknowledge that the results that I'm going to show is the result of a lot of hard work from a lot of people in our group. So although just my name is up here on top. So let me start with this picture, which may be familiar to you, which sort of represents the amount of water that's on the planet. So when you look at water, when you look at the Earth, it's a water planet. There's plenty of water, but in reality, the amount of fresh water available is very small. So of all the water in the planet, about 97% is saline water, as you know, and only about 2.5% is fresh water. And of that fresh water, almost all of it is, about 70% of it is locked up in glaciers and ice caps. And then of the remaining 30%, majority of it is also available to us as groundwater. So the water we see in the surface water bodies in rivers and lakes, it only is about 1%, 1.2% or so. So it's sort of, I like to show this picture because it's sort of a ground reality that despite the idea that there's a lot of water on the planet, the availability of fresh water is actually quite very small. So therefore, we need to be careful about the appropriation of water. And that's also why understanding the variability of the available fresh water becomes important so that we can manage its use more carefully. So this is where our quantification of the fresh water and its components becomes important. So if you understand how much of these water cycle, how the water cycle is changing and what's the variability, then it's sort of we have a better, we can plan better to manage these resources. So this is an example of one of those quantifications where we use modeling and remote sensing tools to understand and quantify the uncertainty and the variability of different water cycle components. And this estimate of the global mean water fluxes and their uncertainty, which is shown in this plus minus terms, was done at a global scale, at an annual sort of time scale. And if you look at the estimates, you may notice that these uncertainties are generally small compared to the mean fluxes. So for example, the evaporation the global mean evaporation is estimated to be about 70 plus or minus 5. That uncertainty looks small. But in reality, when we go down to a finer time scale, so if you do the same estimate at a much finer time scale, at a daily time scale, this uncertainty grows quite a bit, which is telling us that, look, we may understand some of these terms at a larger spatial and time scale, but to understand their variability at a finer time scale, we need to do better. That's where having observations and better modeling tools come in. So, and again, this requires no specific notice, particularly to people in the South Asia region, that the most noticeable impacts of climate change will be on the changes in water cycle and their variability. So this is where NASA has a ton of resources and assets for studying the water cycle. So this schematic shows NASA's current Earth fleet. Consists of many satellites and missions that study different parts of the water cycle, including land cover and land use change, precipitation, evaporation, soil moisture, groundwater, and so on, and many of which are either forthcoming or in the near future. So now, just a quick go view at some of these key satellites. So again, I assume you are probably familiar with the Global Precipitation Measurement satellite. It's a constellation of satellites that that measures rainfall around the world. So by combining the measurements from many different satellites within a constellation, we are able to piece together a picture of precipitation patterns around the world at every 30 minutes, which is what you are seeing in this movie. And similarly, looking at the other water cycle components, NASA launched a satellite called Soil Moisture Active Passive Mission in 2015 that provides global mapping of soil moisture states. And again, here you see an animation of visualization of SMAP providing measurements of soil moisture around the world. And then there are other satellites that looks at different parts of the water cycle. And so this, again, you may be familiar with this, a twin satellite system called Gravity Recovery and Climate Experiment, or GRACE, that is able to infer changes in the water storage deep underground. And GRACE observations have been revolutionary for hydrology in that they have provided a better understanding of some of the changes in the deeper aquifers. So remember that figure in the beginning, which showed that of all the available fresh water, about 30% of it is in groundwater. So therefore, and this is something that we don't see with our naked eye, right? So often when there is a scarcity of water, we tap into our groundwater resources. And I think of it as a long-term bank account that we should be careful about exploiting. So this is an example over California in the US, where GRACE measurements have shown significant depletion in the groundwater resources. So in particular, the last 10 years, California had many significant droughts. And during that time, you can see that the groundwater exploitation has been more significant. So having these sort of measurements provides you that holistic view about some of the major changes and trends that has occurred to our key water storage resources. And NASA again has other satellites that looks at other components of the water cycle. So there are visible or optical instruments that looks at the snow, which is a huge source of water storage for many mid-latitude regions, including the high mountain Asia and the South Asia region. Sorry, going in the wrong way. And then again, these optical instruments can also examine changes in the vegetation condition. So this is a map of vegetation products or greenness products over Africa. And these are analogs of, again, a lot of human interventions on the land surface. So when there is agriculture or irrigation, there is normally a response in vegetation that we can study, or there is deforestation or fires that cause these disturbance impacts. And so it's important to study them, quantify them, and that's where some of these vegetation sensors come in. So now, how do we exploit all these data sets and information that we have? So typically, when we have modeling representation, they look at land surface as a natural sort of setup where it consists of undisturbed vegetation and river bodies and water bodies that are typically unconstrained. But that's not how reality is, where humans have significantly modified the land surface. There is, agriculture, for example, has been documented to change almost 50% of the land surface around the world. And there's urbanization. There is, we have built dams and structures on our water bodies. So unless we capture these human interventions, we are unlikely to really be able to accurately quantify how the water cycle has been changing. So that's where remote sensing, in my opinion, becomes more important, because there's only so much you can do with the conceptual models, which could be limited in representing how some of these human interventions. So let's say you're thinking about agriculture or irrigation. It's really hard to simulate that in a model, because you don't know when exactly the farmer is going to start irrigating, right? But having observations that tell you how this land surface moisture is changing, or how the vegetation responds to irrigation, could really help with teasing out these impacts. So that's where we have been focused on building models and tools that brings in these remote sensing observations and combines with our modeling assets. And at NASA, we have built a system called a Land Information System, or we call this LIS, that essentially provides a lot of capabilities for modeling and data assimilation, which is, like I said earlier, is the technical methodology through which we incorporate remote sensing information within models. So we use that for a lot of scientific research to quantify how the water cycle is changing, what are the human impacts on the water cycle. And this also feeds into a lot of real hydrology applications, quantify the extremes and a lot of times the extremes are in water cycle are tied to issues like food security, how do we manage around hazards and extremes, and so on. So I'll touch on some examples today, but there is a lot of work in this area globally and in different parts of the world. So a word about LIS, Land Information System. So like I said, the key focus is to have these models that, and then bring in remote sensing observations of the water cycle to constrain and improve the model. So over the years, so LIS is a system that has been developed at NASA for in the last 20 years or so. So over these couple of decades, we have built a lot of capabilities for bringing different sensors to constrain it. So we are able to constrain the modeling with precipitation information from different snow instruments, water storage estimates from GRACE and GRACE follow-on. There are estimates of irrigation estimates around the world that we can use. Albedo is another major variable that is essentially the heart of the energy balance, and that can tell you a lot about how the vegetation is changing, how the snow is changing. And as you know, soil moisture is another essential sort of climate variable, and there have been a lot of measurements of soil moisture from many different all these data sets and to constrain the model estimate. So that's the higher level philosophy, how to characterize and improve our representation of the water cycle. So I'll show some examples today. First, over the high mountain Asia region that we call this as HMA, which encapsulates most of the South Asia region. So in fact, NASA has a high mountain Asia team, and I guess Javeria, when she was doing her PhD, was part of the team. So I'll show some highlights from this project. So this is the study. Again, requires no introduction to you all. And we are looking at all the river basins that originate around the Himalayas. So as you know, this is super critically important region in the world because as some people call it, this is the third pole, right? Because this is the largest storage. This region represents the largest storage of fresh water outside the polar region. And then it includes countries like China, India, Pakistan, Bangladesh, which is home to a huge population around the world. So having this large population depending on this critical water supply becomes a significant issue, and our ability to understand the water resources and the changes in water cycle becomes very important in that regard. So it's also relevant because the HMA, the High Mountain Asia region, is also experiencing huge changes driven by climate variability as well as human impact. So this is a map of the changes or the trends in temperature from the ERA 5 reanalysis that shows that the significant warming, particularly in the high elevations, that again, this reanalysis is constructed using many different satellite observations, and that documents the significant warming over the Tibetan Plateau and the high elevation areas. So this has a huge implications on how the water, the snow availability and the melt processes are going to happen. So similar to that example I showed over California, this again, northern India and the Indus Basin is also another hotspot for changes in water storage or the reduction in water storage because of groundwater movie. And the map on the left shows that the trends in terrestrial water storage. The red colors indicate the significant depletion, and so you can see the Indus being a hotspot for that, and some of the eastern regions as well. These are all documented to be because of the exploitation for agriculture. And another variable that we have looked at, so the GRACE measurements show that we have been significantly exploiting the groundwater for agriculture, and then we see the corresponding impact on vegetation. So this map on the left shows the trends in leaf area index or vegetation changes, and all the blue colors indicate that the LAI or the leaf area index is increasing in the past several decades. And you can also see that most of those increases are correlated with areas where a lot of agriculture happens. So you can actually see the Indus River basin in this map, and the Ganges Brahmaputra basin, where a lot of irrigated agriculture happens. And this is again, one of the places in the highest in the world where there's the highest increase in the vegetation greening rate is happening, and it's projected to increase partly because there's a huge population that depends on intense food production and therefore the intense agriculture that needs to support it. And so we looked into this further, so to really tease out what are the causes of greening. Typically, there's a laundry list of reasons for greening features around the world, from CO2 fertilization to afforestation in some places, or increases in soil moisture, which is one of the main common factor, which is driven by irrigation or increased availability of precipitation. And also warming could lead to more greening, because when there is a climate-induced warming, that means you have longer growing seasons or more optimal temperature for plant growth. So over this HMA region, we applied partial information decomposition analysis, which is based on an information theory approach. This schematic here shows how essentially we tease this out. So we are looking at the information in LAI, or leaf area index, and driven by either, in this case, we just focused on soil moisture or snow based inputs. So if there is warming, that generally there's less snow, which promotes the longer growing seasons and so on. So you can think of it as a sort of a Venn diagram, right? So the total available information for vegetation or leaf area index is shown in this green circle, and some of which is contributed by changes in soil moisture, some of it's contributed by changes in snow cover. And then you can also think of this information, some of this information in LAI, which is enabled by a combination of by using both these information simultaneously, and some which is only uniquely informed by soil moisture. So kind of teasing this out using this approach, we can understand how much or which parts of the high mountain Asia is the greening is happening because of the changes in soil moisture, in which parts the greening is happening because of the changes in warming or snow changes, and so on. So long story short, so if you apply this analysis, the map of the greening drivers looks like the following map here, where all the red areas are where the greening is driven by warming or reduced snow cover, which promotes longer growing season. And then you can also see many places over the high mountain Asia where irrigation or agriculture is a significant driver of the greening. So again, some of the usual suspects pan out here. So you can see the Indus River Basin, Ganges, Brahmaputra. These are places where the greening is primarily driven by irrigation. And then there are some places where precipitation also drives that greening, which is generally limited in this domain. So in most places, it's driven by either warming or irrigation. So in other words, this shows a significant human footprint on the water, the greening aspects and the water availability, right? Either because of the agriculture or because of climate variability and the warming that comes with it. We also looked at we did a similar analysis for surface albedo changes, which is, like I said, is a very important variable for surface energy balance that determines how much radiation is partitioned as net radiation available at the surface. If you look at the long-term changes in surface albedo, and this is a visible component of the broadband albedo, you can see some interesting patterns. In the southern parts of this domain, there is generally a decrease in surface albedo. And in the higher elevation, you see an increase in albedo as well. And again, if you apply that partial information decomposition analysis, you can try to understand what are the factors that drive some of these variability. So you can see in many places, snow cover changes are driving the changes in surface albedo. And in some places, the vegetation patterns and the significant agricultural activity is a big driver of the albedo. And so we put all this together into a reanalysis where we assimilate all these products and then try to, and again, look at some of the understandings that comes with it. So one of the things we looked at is a process called rain on snow, which, as you know, has major impacts on how much water available downstream is impacted. So over the whole high mountain Asia region, this is our assessment of where the rain on snow events are happening more, and how much of it is happening, which is on the right here. The panel shows the number of rain on snow days per year. So based on our analysis in the past 2 decades, and these are some of the hotspots of rain on snow. And in many places, you have more than about a month plus of rain on snow events happening. Majority of them in the western side here. And we also looked at how this changes the availability of water for runoff, right? So when you have rain happening on snow, that melts the snowpack quickly, and that changes the face of the water availability. So if you have more rain on snow events happening, that's likely to lead to more extremes, changes in the face of stream flow in the rivers and so on. And if you look at the trends in rain on snow, we see some interesting patterns. Over on the western side and the Indus areas, we see a decrease in rain on snow. And therefore, that sort of implies a reduction in water availability. So you have less rain on snow events happening. That means less snowpack. Rain on snow is leading to less melt and reduced water availability. Whereas on the right side, we see more rain on snow. I'm sorry, I got this flipped. So on the left, you see an increase in the Indus River Basin, which means you have more rain on snow events happening, which means you have the likelihood of extremes and floods and landslides is increasing. But on the Ganges Brahmaputra region, it's the other way. You have less instances of rain on snow events. So now I'll just, before I finish, I want to show a couple of higher level focus studies. There's a project called the Earth Information System, which is taking some of these inferences we have at a larger global scale, and then trying to piece together some of these inferences that are provided by remote sensing to understand how the human management is impacting water availability. How are the extremes and like droughts and floods changing, and how does it impact our water availability, both at short time scales and at longer time scales? And just to underscore that point of why remote sensing, piecing all the information we have is important. This is an example that we did over the Midwest US. In 2019, there was a huge flood that impacted a lot of Midwest region in the US. And this is where a lot of agriculture happened. So this was an unfortunate coincidence of many different factors. So first of all, there was huge rainfall, and that happened as a rain on snow event. And prior to this rain event, there was a lot of snow on the ground. So all this rain happening on top of the snowpack led to a huge flood. So having remote sensing measurements was critically important to piece together this puzzle. So we had huge rainfall that was captured by GPM, a global precipitation measurement, and then the anomalous snow that we had on the ground was enabled by assimilating data from AMSR2 instrument. And then our modeling system was able to then predict that big flood that happened in this region. So that didn't stop there. So once we had this huge flood, the soils were wet all over that region. And this is a map of that region with the wet, the red, the blue colors indicating places where soil moisture was significantly better. And because soils were too wet, the farmers delayed their planting. And that was also captured by our data set that sensors that measure vegetation changes. So altogether, this event, it's a one event, had a huge economic impacts. And in that year, the US, the government issued damages, or the economic damages on the order of $33 billion. So it sort of showcases why, if you're able to do this in real time and take advantage of these measurements, we could plan better around some disasters like this. Again, another example over Bangladesh that we have been studying, an area where there's a lot of complicated impacts on the water cycle. So there is sea level rise and loss of land, and this is enabled by radar altimetry measurements that document these things. But upstream, again, there's a lot of changes in the water cycle because of the, again, intense agriculture. There's huge groundwater exploitation that documented by Grace, and working with some of the scientists in Bangladesh, we were able to confirm these findings, where the groundwater data sets confirmed that big decline. And this is also happening while there is an overall reduced water availability. So GPM data shows that there is a declining trend in precipitation. So this is a huge issue. So you are exploiting groundwater, your long-term bank account, at the same time when there is an overall decline in water availability from precipitation because of the climate variability. So having this sort of synthesis is important to have better tools to plan around our declining water resources. So we've been doing this also at a global scale. This is a map of, again, what we call as non-stationarities in the water cycle. So there is changes in water cycle because of increasing or decreasing trends in some variables, but at the same time, these human interventions as well as climate change has led to shifting of seasonality of some of the variables, more extremes in some variables. So we put all this together as a measure of non-stationarity in the water cycle, and these are some of the regions that we picked out as hotspots. So the study, which is about to be submitted, shows some interesting things, that in majority of the world, these non-stationarity patterns are driven by increasing or decreasing trends, and as well as seasonal shifts, because things like rain and snow or agriculture, it actually shifts the seasonality of vegetation and water cycle components. And also in some places there are significant changes in extremes with, again, strong regional patterns. So before I end, I wanted to show that NASA, this is the year of open science for NASA. As you know, all the NASA datasets are free and available to the entire world. We're also making a huge effort to make the science more open and available to the world. So there is a data portal or a portal where we communicate science called VEDA, which stands for Visualization, Exploration, and Data Analysis. So there's a link here. You are able to see some of these science stories being developed, and we are able to contribute to it, provide your comments, bring in the local expertise, and work with the NASA scientists through this. So I'll just end by saying, land surface, studying the land surface is exciting, because this is where we live, right? And this is also where the direct and the consequential impacts of climate change will be, because this is where we face water shortages. This is where we have to manage the extremes. And this is also why having a remote sensing information is super critical, because without which we won't be able to understand how these changes are happening, where these changes are happening, how we can manage around them. So we encourage and we really invite the broader scientific community and local experts like you to work with us and help us improve our understanding that's provided by these, global products. And and again, thank you for inviting me today, and I'll look forward to working with some of you.
Thank you very much, Dr. Kumar. That was a wonderful presentation, and thank you particularly for sharing your information and your projects with us. So let's start the question and answer session. If any of the participants have any questions, please feel free to write in the chat box. Otherwise, you can just send them to me as well. I have received one question, so I'll begin with that. One of my students is actually asking, can we participate in the NASA products such as EIS, or how can students become involved in different initiatives that you've shared?
Yeah, so like I said, there is a lot of new exploration websites and activities coming. So one of them is called this Veda stuff. So you can actually go and so in theory, anybody with an access to the earthdata.nasa.gov should be able to participate. I just have to say that this is still in infancy, so it may take a few more months before it can actually be opened to the entire world and allow people to participate. But the idea is we are moving to a place where all the data sets will be under the cloud. I don't know if you've used things like Google Earth, right, or Google Colab, where the data sets are there, and then you just focus on doing the discovery and the analysis of the data. So it's sort of similar in that concept, except that it's going to have all the NASA products there, the tools to work with it, and some of the scientific expertise that comes with it. So I wish I could show you one of these, but you can go and check out these yourself, where there's that story on Bangladesh we did. So how, for example, that story was developed, what sort of data sets were produced, and how did we do that? And there are examples of Jupyter notebooks that show how exactly did we look at the groundwater trends, right? And then a student or a researcher can then take that and apply this for your own region and build on it without necessarily having our intervention, and then come back and tell us what you found, right? What are the exciting things you discovered, or what are some of the limitations you found, and why exactly, and this is where I think having that local knowledge or expertise become very important, because there are some processes or that we may not be aware of, right? Or that's not, we're not thinking about it while doing this analysis, but the local experts are able to tell us, well, this is why it's happening. And that way we can, I mean, this is the way we expect the science to be improved, and working with the local experts and scientists. Hopefully that helps you answer.
Yeah, thank you for your answer. So I have a little bit of a technical question here, and this is about the Mana et al. Study that you showed, in which we had precipitation that was enhancing the greening in high mountain Asia. So the question was, when you talk about precipitation, are we talking about just snow or just rain, snow and rain? And in which context are we taking the definition precipitation in this particular study?
Yeah, so in this particular one, we consider the total rainfall, which is rain and snow, and then the models then have, they partition that into rain and snow internally, again based on air temperature changes that we expect. But when I talked about precipitation, that the total precipitation.
Thank you. So there's another question by a participant. And it talks about connecting the science that you do then with policy making. And how can the remote sensing information be used in policy making, and how to reconcile the uncertainty among different platforms to develop a bigger picture for data-driven policy decisions?
Yeah, so that's something I will have to defer because NASA is a research organization. We are actually strictly prohibited from engaging in policy decisions. So our job is to describe the science and describe what we are seeing, and hopefully that will lead to policy making. But so the way we do this is by engaging with climate authorities and organizations that are supposed to be using the information that we provide to make policy. So for example, the World Meteorological Organization, WMO, relies on some of the products that we are using. And so they produce a state of the water cycle report every year, right? And they make recommendations. So in other words, we provide them the information, and then organizations like IPCC or WMO, they interpret that and say, look, this is what we need to do, or this is how we manage around it. So strictly speaking, NASA is not allowed to say, well, this is what you should be doing, right? We can say what our science is, and that's where we have to stop.
Thank you for your answer. So I have another question here, and it's a participant is asking, so what are the latest softwares and tools for hydrology analysis? So I think there are a number of tools available, but what the participant is asking, what is the state of the art in terms of hydrology, so that we can avoid conventional or old methods that do not work anymore?
Yeah, that's an interesting question. So there is a lot of tools out there. So I can speak to the NASA side, where systems that I described, the land information system, which is a framework, and that includes many the state-of-the-art modeling systems in it. So we are not prescribing one set of tools. So it includes some of the more modern land surface models, some of the more modern hydrology models, and obviously all the tools for remote sensing and data assimilation. But that's just still a small part of the whole spectrum. There's a huge academic community out there. They are working on newer tools. So there's obviously machine learning is a big deal. And again, machine learning tools have been used to infer, or they've been shown to do better in some cases in terms of learning these complex changes and patterns and non-linearity. So I think, in my opinion, it's important to look at all these things together, right, and not be sort of committed to only one way of doing things. And there's advantages to be gained by working across these different classes of models and different classes of tools. So machine learning, for example, can be an important benchmark in many cases, but it may not tell you exactly how the right answer was developed. Right? But then that's where the models can be used in concert with some of the inferences that we are getting from machine learning to then do that scientific discovery. Why exactly did we get a better modeling result, and what are the processes behind it? What are the contributions of the human interventions and climate variability and those type of things. I don't know if I'm answering the question.
Yeah, you are. Thank you for your answer. So I'll, in the interest of time, I'll just include one last question. And this is perhaps a tricky question, but feel free to answer it however you think is correct. So the question is that if we want to collaborate with NASA for establishment of a local or ground validation center, so does NASA support initiatives led by local government institutions?
Yeah, of course. I think we do. So we have many examples around the world, and most of this, the way typically we collaborate is through data or scientific expertise, sharing that openly and freely. Like I said, all NASA datasets are free for the entire world to use, and we are working hard to make the science open again to the entire world. And so NASA has declared 2023 as a year of open science, which means we basically make the science open and available while it's being produced and not after it's done, right? The typical practice is to work on the science and then you publish it and then you make it available. But that we are trying to change that paradigm while to describe how the science is being done while it's being done and make it available to the community so that people can engage. So anyway, I think working with international organizations are typically harder in terms of exchanging funds and whatnot, but a great place to start is by sharing our scientific expertise and data sets. And we have lots of examples of that around the world. And that's led to, some fundamental insights on changes in water cycle. So for example, that study that I showed over the northern India, that was developed 10 years ago, right, when GRACE data was launched. And a lot of hydrologists thought that, well, GRACE is too coarse to be of, in terms of the spatial resolution to provide valuable information for hydrology. But then it uncovered these fundamental changes in, groundwater exploitation in many parts of the world, right? And that a study over northern India was one, and after that, similar studies have been applied in many parts of the world. And because we know some of those big changes, that has led to policy changes in terms of how we exploit groundwater and so on. So I think a lot can be done starting with the data and working together, and then I think that's probably is my response.
Thank you very much for your answer. If anyone has any other questions, you can email them to the center. So you can either email them to me or you can email them to the center's official email, which is included in the registration. Thank you very much to everyone for attending this talk. I'll stop the recording now. And Dr. Kumar, if you can just be there for a couple of minutes, then we would appreciate that.